Previously, we have seen how both straight lines and circles can be represented as equations. In this video, we're going to take advantage of this representation to find the points where a line intersects a circle. Now, intersecting two geometric objects is obviously quite useful to us. Whilst in this case we're working with fairly simple equations in 2D, a similar approach can be used with more complex equations in 3D to intersect rays with 3D geometric objects in a ray tracer, for example. So in this video we're going to be taking a look at what I believe to be the most obvious, but perhaps not the most efficient, approach to solving this problem. In the next video, we're going to approach the exact same problem again, but we're going to take a slightly different perspective. And I believe that's going to allow us to derive a more efficient solution to the problem. So in this video, if we recall back to our earlier videos, we'll remember that the equation for a straight line is y is equal to mx plus c. And we'll also recall that the equation for a circle that is centered around the point AB is x minus a squared plus y minus b squared is equal to the radius of the circle squared. So let's draw a circle on the whiteboard really quick, and I'm not going to worry about labeling the circle or drawing axes. I'm just going to draw a really rough circle. There we go. Now, an infinitely long line could intersect this circle in a number of different ways. Firstly, we could have a line that passes straight through the circle. If that's the case, if it passes right through the circle, we know it's going to intersect that circle twice. Once when it enters the circle and once where it exits the circle. Alternatively, the line might be a tangent of the circle. That is to say, the line passes the circle and just touches it at one single point. So we could have a line that maybe looks like this. I didn't quite touch, but if you imagine it was just touching here at that one point. So it doesn't pass through the circle, it simply touches the circle at one point. In that case, if we had a line that was a tangent of the circle, there would only be a single point of intersection. Our final case could be that the line doesn't intersect the circle at all. If we had a line that came down like this, we'd have no points of intersection. So there are three cases, one where we pass right through the circle and have 2 points of intersection, one where we're a tangent to the circle and have a single point of intersection, and one where there are no points of intersection. Well, in the case of any intersection point, so this guy, or this point right here, in the case of any point of intersection, we know that the coordinates of that point are going to satisfy both our line equation for the line and our circle equation for the circle. That is to say, if we put the x-coordinate of a point of intersection into both equations, it would give us the same y-coordinate out, or vice versa. Now, the way that we can solve these types of problems is actually quite straightforward. We know that the x and y coordinates for an intersection point are going to satisfy both equations. We've just stated that. Thus, we know that the y coordinate, for example, for our line equation would be the exact same value as the y coordinate for our circle equation. So at a point of intersection, we know that this y will equal this y because our point satisfies both equations. Therefore, if we know that these two are equal, and we know that our y for our line is equal to mx plus c, we could take the value mx plus c and we could use it as the y in our circle equation. These two guys are equal. Therefore, if this y is equal to mx plus c and these guys are equal, this y must also be equal to mx plus c. If we take mx plus c and substitute it in for y in our circle equation, we're going to have an equation that is in terms of just x. The only variable in that equation is x because we know a, we know b, we know r, we know m, and we know c. So therefore our only variable is x. That would allow us to solve for this x, solve for the variable by rearranging the equation so that we have x equal to something. And if we can solve for x, then that allows us to be able to find the point or points of intersection in x. We can take that value of x and use it in our line equation to find the corresponding y coordinates of the point or points of intersection. Now, as we mentioned earlier, this approach which we're going to be exploring in this video is the most obvious but not necessarily the most efficient way to solve this problem. You're going to see as we solve the problem that the resultant equation is actually quite lengthy. Thus, if we were to write this as a computer program, it would require a fairly large number of computations to actually calculate. In the next video, I'm going to present a different way of thinking about this problem, which I believe is far more useful for approaching problems of many kinds, not just this particular problem. And it also results in a slightly more efficient computation. But that's in the next video. In this video, we're going to take the most obvious approach. And the most obvious approach is to simply take mx plus c and substitute it in for our value of y. So I'm going to bring up a new whiteboard just so that we have as much room, because this is a fairly large substitution and rearranging. So we saw that y is equal to mx plus c, and we saw that x minus a squared plus y minus b squared is equal to the radius squared. So we're going to take mx plus c, we're going to substitute that in for y. That's going to give us x minus a squared plus mx plus c minus b squared is equal to r squared. Now this is going to be a fairly lengthy expansion. It's not hard, but because it's quite a long-winded procedure, that means there's going to be room for mistakes to be made, for errors to crop up. So I'm going to take my time here, but the important thing is when we're squaring expressions like this, squaring brackets, that we make sure that every term inside the bracket gets multiplied by all of the terms inside the bracket. Now, to make this a little more clear, I'm actually going to add a few extra stages in our working than I usually would when I would be expanding this in my own time. I'm actually going to add a few extra stages of working just to avoid losing anyone with the expansion. So hopefully you can follow along very clearly with what I'm doing here with the expansion. So the first thing we know is if we have something squared, it's the same as having that multiplied by itself. So x minus a squared becomes x minus a multiplied by x minus a. Then we're going to add mx plus c minus b all squared. So that's the same as having mx plus c minus b multiplied by mx plus c minus b, which is equal to r squared. So now we said that every term inside a square must get multiplied by every term inside the square. So for this example, that means that we need to take x multiplied by x, which we know is going to give us x multiplied by x. Usually I just simply write that as x squared. In this case, I want to make it very clear what we're doing here. So x multiplied by x, then x multiplied by minus a, so plus x multiplied by minus a. Then we're going to take the minus a in our first bracket because we've multiplied x by everyone. So minus a multiplied by x plus minus a multiplied by minus a. So that's our first set of parentheses multiplied out. Then we're going to add to that these guys multiplied out, so I'm going to do that on a new line. So we're going to start with mx. I need mx multiplied by mx. Add to that c, mx multiplied by c, because we're still doing mx from our first bracket. So mx multiplied by c. Add to that mx multiplied by minus b. Add to that c multiplied by mx. Add to that c multiplied by c. Add to that c multiplied by minus b. I'm going to scroll down just a little bit. Then we're going to add to that minus b multiplied by mx. Add to that minus b multiplied by c. Then we're going to add to that minus b multiplied by minus b. which is equal to r squared. If we now start actually multiplying these through and being careful where we have double negatives, for example, minus a times minus a will become positive a, minus b times minus b will become positive b. If we start multiplying that all out, we should start to see some form of equation that we might be able to solve. So this first term is going to become x squared plus, well, x times minus a is going to be minus ax, so I'm actually going to write minus ax. Again, we've got minus a times x and minus ax, so that's actually going to become a minus ax. Minus a times minus a is going to give us plus a, plus mx times mx is going to be m squared x squared, so plus m squared x squared, plus mx multiplied by c is going to be, we could say mxc. I'm actually going to say cmx. When we've got multiple letters multiplied together, I'm going to try and keep the x at the very rightmost side and then all the other letters in alphabetical order. And that's just going to help when we've got things that are actually the same term, which we can then start to collect together, whereas if I'd just simply done them in the order that we have them here, I'd have a term here that was xa, another term that was ax, and we might not see that they are indeed the same term. So again, what I'm simply doing is making x at the very rightmost, and then everything else in alphabetical order. So we just did m squared x squared, so we're going to add to that mx times c, which is going to be cmx. We're then going to add to that mx times minus b. That means we're actually going to subtract bmx. We're then going to add to that c times mx, so cmx. Notice because of the way we're now ordering these alphabetically, I can see these are the same, which means eventually we're going to have two of those. So plus cmx plus c times c is c squared. C times minus b is minus bc, plus minus b times mx is minus bmx, so that's that guy, plus minus b times c is minus bc, plus minus b times minus b is plus b squared, so plus b squared is equal to r squared. Okay, we're making some nice progress here. So what I want to do now is collect the like terms. That is to say, we have minus ax here, minus ax here. What I want to do is write that as minus 2ax. So x squared, we only have a single x squared on its own in the entire equation, so that's just going to be x squared. We have minus ax. We actually have another minus ax here, and that's the only ax's that we have in our equation, so that's going to become minus 2ax. And I'm actually going to start checking these off as I'm adding them to the equation so that I don't miss anything. Then we've got plus a, and that is the only a that is in there, I believe. So I think that a actually should have been plus a squared, so my apologies. See how I said it's so easy to make even simple mistakes that would mess us up later on? This minus a times minus a would of course be plus a squared, so that is plus a squared. My apologies if that confused you in any way. I simply missed the squared off when I calculated that. So this should be plus a squared. We only have one of those a squared, so plus a squared. M squared x squared is the only instance of m squared x squared, so plus m squared x squared. We have cmx, we actually have another cmx, they're the only two cmx's, so plus 2cmx, get rid of those. We have minus bmx, we actually have another minus bmx here, they're the only two bmx's, so that's going to be minus 2bmx. Get rid of those. Plus c squared, that's the only c squared that we have, so plus c squared. Minus bc, we actually have two minus bc, so that's minus 2bc. Get rid of those. Plus b squared is equal to r squared. Fantastic. So now that we've collected our like terms, we actually have a simpler equation to work with. I'm going to rearrange this slightly so that I collect our x squareds first, then our x's, then our constant numbers. I'm also going to subtract r squared from both sides so that we get r squared on one side and this equation equal to 0. Hopefully, if not after this step, then after the next step, you're going to see exactly why I'm doing that. So I want to collect our x squareds together, so x squared, and our only other x squared is m squared x squared. So x squared plus m squared x squared. And that's going to then leave us with terms of x, so minus 2ax plus 2cmx minus 2bmx. I believe that's our only x's, so we've done x squared, we've done m squared x squared, minus 2ax plus 2cmx minus 2bmx. Yep, nothing else has a term of x. Now we just have our constants, so it's going to be plus a squared. I'm actually going to write plus b squared next. The order, of course, here doesn't matter, but I think it just reads more nicely if we have a squared plus b squared plus c squared minus 2bc. And of course, I want to subtract r squared from both sides so that it is equal to 0. So now that we have this, I can factorize in terms of x. And hopefully this is now going to make it very clear where I'm going with this. So x squared, well, we have 1x squared here plus m squared minus x. What do we have? Well, I'm going to actually say plus x. What do we have here? Well, we have minus 2a plus 2cm minus 2bm. And then we can collect all these into a bracket, so plus a squared plus b squared plus c squared minus 2bc minus r squared is all equal to 0. So what have I done here? Well, I've actually written this in the form of a x squared plus bx plus c is equal to 0. Now, I've used capital A, B, C just to distinguish from the lowercase a, b, c we already have in our equation, but you notice we have a times x squared, where a is going to be this bracket here. So a is equal to 1 plus m squared. We have b times x, where b is going to be equal to this bracket here. So b is equal to, I'm actually going to write our positive 2cm first. So 2cm minus 2a minus 2bm. And then c is this constant term here. So c is equal to a squared plus b squared plus c squared minus 2bc minus r squared. And that allows us, of course, because we've got it in this form of ax squared plus bx plus c is equal to 0, we can solve this using our quadratic formula. Using our formula, x is equal to minus, now I'm going to use capitals, obviously, to keep with using capitals here, minus b plus or minus the square root of b squared minus 4ac all over 2a. So we can use this to solve. Now, just as we saw when we were solving quadratic equations, the value here of our b squared minus 4ac, this is going to determine if there are two solutions, one solution or no solutions to our problem. So if this value is positive, then we know there are going to be two solutions, plus the square root and minus the square root. Now, this is going to occur when I need my other layer. So when that value is positive, that's going to occur when our line passes all the way through our circle and leaves us with two intersections. If that value is equal to 0, then we know that the square root of 0 is always 0, therefore plus root 0 and minus root 0 are both equal to 0. So this is going to occur when we have just a single solution, because we're only going to get minus b over 2a. And in those cases, we know that's when the line is tangential to the circle. It's a tangent to the circle, leaving us with a single point where it touches the circle. Finally, if b squared minus 4ac is negative, well, we know for this type of equation we can't find the square root of a negative number. That means there are no solutions, and that means the line doesn't intersect. So if you were programming this intersection formula, you'd be able to check this value of b squared minus 4ac, and you could use that to determine how to continue. You could use that to determine, do we need to find two points by finding the square root of b squared minus 4ac, adding it, subtracting it? Do we need to find one point of intersection by taking just minus b divided by 2a? Or are there no points of intersection and we can't continue? Now you notice in this case there's actually no way that we can get a divide by 0. A is here is equal to 1 plus m squared. M squared, because it's a number squared, is always going to be greater than or equal to 0. It can't be a negative number. A square can't be negative. If we take even a negative number and multiply it by itself, it's the same negative number, it becomes positive. So m squared is always greater than or equal to 0. That means 1 plus m squared is always greater than or equal to 1. It can never reach 0, so 2a is never going to be 0. Now again, this is quite a lengthy formula. A is nice and simple to calculate, 1 plus m squared, but b and c, they require quite a number of computations to calculate that value before we can even insert them into our quadratic formula. But let's test our formula with some examples and see if it is indeed working correctly. So I'm going to bring up a new whiteboard. And I'm going to draw a simple example. So let's say that I'm only going to draw this small because it doesn't need to be accurate. But let's say that I've got some Cartesian axes in 2D. And let's say that I've got a circle that's centered around the origin and it's going to have a radius of 1. So let's say that that was 1 unit in the positive and negative x and y directions. That would give us a circle that looks something like this. Please bear with the fact that my drawing on the Wacom tablet is a little dodgy at best. We could maybe erase this guy here. So we have a circle that is going to have a radius of 1 unit. And let's say that we have a line. Now what I'm going to do to test the equation, I'm going to choose 2 points of intersection that I know exist on our circle and use those 2 points to define our line. So in this case I'm going to take this point up here, which we know is 0 in x and 1 in y, and I'm going to take this point here, which we know is minus 1 in x and 0 in y. If we connected those points with a line, well, we know that this is going from minus 1 in x to 0 in x, and in that step of 1 in x, it's going up 1 in y. So that means our gradient, m, is equal to 1, so y is going to be equal to x, plus our intercept here, where we cut the y-axis, is 1. So that means this line has the equation y is equal to x plus 1. So what is the information for our equation, our intersection equation? Well, we know our gradient m is equal to 1. We know that c, our intercept, is also equal to 1. A and b, the center of our circle that's centered around the origin, so a is equal to 0, b is equal to 0, and the radius of our circle is equal to 1. So what we can do, we can now take this information and we can plug it in to the equation that we just saw. So we can calculate a, b, and c, and then plug them into our quadratic formula. So we saw that a is equal to 1 plus m squared. So if a is equal to 1 plus m squared, it's going to be equal to 1 plus 1 squared, which is equal to 2. So that's our value for a. B is equal to, well, let's jump back and see what b was equal to. So b is equal to 2cm minus 2a minus 2bm. So b is equal to 2cm minus 2a minus 2bm. So we can put our numbers into that. So that's going to be equal to 2 times 1 times 1. So 2c is 1, m is 1, minus 2a is 0, if you recall, we're centered at the origin, minus 2, b is 0, m is 1. Well, 2 times 1 is 2, minus 2 times 0 is going to be 0, minus 2 times 0 times 1 is going to be 0, which means that b is equal to 2. And then finally we need to calculate c. If we jump back and take a look at what c looked like, we saw c is equal to a squared plus b squared plus c squared minus 2bc minus r squared. So c is equal to a squared plus b squared plus c squared minus 2bc minus r squared. If we put our numbers into this, that means c is equal to 0 squared. Oh, not 0 to the power of 0, 0 squared. Plus 0 squared, plus our intercept was 1, so 1 squared, minus 2 times b is 0, c is 1, minus r, if you recall, our radius is 1, so minus 1 squared. That means c is equal to 0 squared is 0, plus 0 squared is 0, plus 1 squared is 1, minus 2 times 0 times 1 is 0, minus 1 squared is minus 1. So c is equal to, well, 0 plus 0 is 0, plus 1 is 1, minus 0 is 1, minus 1 is 0. So c is equal to 0. So again, a is 2, b is 2, c is 0. So a is equal to 2, b is equal to 2, c is equal to 0. We can now take these and plug them into our quadratic formula. So again, what do we know about our quadratic formula? We know that x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. So the first thing we're going to calculate is b squared minus 4ac to determine how many points of intersection do we have. So b squared minus 4ac is going to be equal to, well, b squared is 2 squared, minus 4 times a is 2, c is 0. That means that that's going to be equal to 4, minus 4 times 2 times 0 is 0. So this b squared minus 4ac is equal to 4. That's positive. That tells us there are 2 points of intersection, which is a good sign that we're on the right track, because we know there are 2 points of intersection when we designed this problem. So b squared minus 4ac is equal to 4. Let's solve the rest of this equation. That means x is equal to minus b, well, b is 2, so minus 2, plus or minus the square root of b squared minus 4ac, so the square root of 4, divided by 2 times a, and if you recall, a was also equal to 2. So as we start now calculating this, as I run out of space, I'm going to try and squeeze this in. So x is equal to minus 2 plus or minus the square root of 4 is 2, so plus or minus 2 divided by 4, which means that x is going to be equal to either minus 2 plus 2 over 4, or it's going to be equal to minus 2 minus 2 over 4, which means we're either going to have it equal to 0 over 4, or it's going to be equal to minus 4 over 4, which means that x is equal to 0, or it's equal to minus 1. If we jump back up to our problem, x was equal to 0, or it's equal to minus 1. Fantastic. So we found our x coordinates. X is equal to 0 or minus 1. Now, rather than jumping to a new whiteboard, I'm going to cheat a little bit and just continue up here. So x is equal to 0 or minus 1. We plug those back into our line equation. That means that y is going to be equal to 0 plus 1 or minus 1 plus 1, which means y is equal to 1, or it's equal to 0, which gives us the point of intersection as 0, 1, or in actual case, we know there's 2, so in actual fact, the point of intersection is both, so we can say and. So it's 0, 1, and the other point of intersection is minus 1 and 0. So here we can see 0, 1 was a point of intersection. Yes, it was. Fantastic. And minus 1, 0 was the other point of intersection. Yes, it was. Fantastic. So we can see that our equation is indeed working correctly, and that's exactly what we wanted to see. So let's perform a second test case where instead of having it centered at the origin, we have it centered at some other point. So I'm going to bring up a new whiteboard layer, and you're going to get the opportunity to see how we can use this equation again, but for a slightly more complicated example. So I'm going to draw another set of Cartesian axes. Here's x, here's y. And in this case, I want to center our circle around the point 2, 4. So let me say that that's 4 in y. That means this is going to be roughly 4 in x. That's going to be roughly 2 in x. So that's going to be the center of our circle. I'm going to say the circle has a radius of 2. So if this is 2 in x, we're going to touch here in y. We're going to touch 4 in x over here. We're going to come down 2 and up to like so. And then I'm going to try and draw this circle in roughly. Fantastic. So there is our circle. It has a radius of 2 and it is centered at the point 2, 4. So this is 2 in x, 4 in x, 4 in y. This is going to be 2 in y and 0. Fantastic. So it's centered at the point 2, 4. And I want a line that's going to intersect this at 2 points that are predictable. So I'm going to say I want a point of intersection here at 0, 4. And I want another point of intersection here at 2, 2. So we're going to have a line that passes through these points. What do we know about this line? Well, we can see if I was traveling 1 unit in x, or more easily to see, if I was traveling 2 units in x, I've traveled down 2 units in y. That means for 1 unit in x, I'm traveling down 1 unit in y. That means my gradient is equal to -1, and we can see our intercept is equal to 4. That gives us the equation y is equal to -x plus 4. Fantastic. So now that we've got that, let's go ahead and actually write all the information that we know. So we know that m is equal to -1, c is equal to 4, a is equal to 2, b is equal to 4, because A and B are our center point of the circle, and we know that our radius in this case is actually equal to 2. So we've got all that information. We can now calculate A, B, and C with these. So A was equal to 1 plus m squared, which is equal to 1 plus -1 squared, which is equal to 1 plus 1, which is equal to 2. So A is equal to 2. B is equal to 2cm minus 2a minus 2bm, which is equal to 2 times 4 times -1, minus 2 times 2, minus 2 times b is 4, m is -1, so that's equal to 2 times 4 is 8, times -1 is -8. 2 times 2 is 4, so -4. 2 times 4 is 8, times -1 rather is -8, times the negative here becomes +8. So hopefully you can see that our -8 and +8 here are going to add together to form 0, meaning the result is -4. So B is equal to -4. Finally, C is going to be equal to a squared plus b squared plus c squared minus 2bc minus r squared. So that's equal to a is 2, b is 4, so 2 squared plus 4 squared plus c was 4 plus 4 squared minus 2 times b is 4, c is 4, so 2 times 4 times 4 minus our radius was 2, so minus 2 squared. That's going to give us 4 plus 16 minus 4 times 4 is 16 times 2 is 32, so minus 32 minus 2 squared is 4. Well, 16 plus 16 is 32, minus 32 is 0, so those cancel to 0. And 4 minus 4 is 0, so everything here actually results with C having a value of 0. So C is 0. We saw that A, in this case, is equal to 2. And we saw that B is equal to -4. So A is equal to 2, and B is equal to -4. So now that we've got these, let's put them into our quadratic formula. So we know that x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. So the first thing we're going to calculate is b squared minus 4ac. So b squared minus 4ac is equal to -4 squared minus 4 times a is 2 times c is 0. Well, we can see that minus 4 squared is going to be 16. Minus 4 times 2 times 0 is 0. So b squared minus 4ac is 16, which means that this is positive. It gives us 2 points of intersection, which we were expecting. Fantastic. So we can now continue to find those points of intersection. So x is going to be equal to minus b, we saw was minus 4, so it's equal to minus 4, plus or minus the square root of, we saw b squared minus 4ac is 16, divided by 2 times a, and a we saw is a value of 2. So 2 times 2. I'm going to write this next to us just so we have enough room to evaluate all this. So minus 4 is plus 4, so it's equal to 4. Plus or minus the square root of 16 is 4. So 4 plus or minus 4 divided by 4. That means that x is going to be equal to 4 plus 4 over 4, or 4 minus 4 over 4, which means that it's equal to 8 over 4, or 0 over 4, which means it's equal to 2, or 0. If we take a look at this, 2 or 0 in x, well, this point here is 0 in x, 4 in y, and this point here is 2 in x, 2 in y. So 0 in x or 2 in x. So far, we are on the right track for finding the coordinates of our points of intersection. So we need to take those and plug them into y is equal to minus x plus 4. So y is equal to minus x plus 4. That means that y is going to be equal to either minus 0 plus 4 or minus 2 plus 4, which means it's equal to either 4 or 2. Now let's make sure that we get these paired up correctly. So when I took 2 and used that as x, we got a y as 2. So our point of intersection is 2, 2 there. When I took 0 as that, as x rather, and added 4 to it, I got 4 in y. So the other point is 0, 4. So our 2 points of intersection are 0, 4 and 2, 2. 0, 4 and 2, 2. Fantastic. Our points of intersection are matching our diagram, which means that our equation appears to be working correctly. Fantastic. So whilst putting numbers into an equation, as we've seen here in 2 examples, is very simple, I am actually going to set you just one question to work through on your own. Now I'm going to be setting the same question as well as using these same examples in the next video. So hopefully this is going to help you to get a comparison for how much quicker it's going to be to solve the problem using the method in the next video as opposed to the method in this video that has quite a lot of calculations. It's also going to help us in the next video to make sure that our new method is giving us the same results as the method that we've developed in this video. So I'm going to set a question for you guys. And that question is going to give us that we have a line with the equation y is equal to minus x plus 11. And we have a circle that has the equation x minus 3 squared plus y minus 5 squared is equal to 9. Does this line and this circle intersect? Do they intersect? And if so, what are the points of intersection? So go ahead and pause the video. Give this an attempt. If you get stuck or once you have a solution, unpause the video and I'm going to work through this here on the whiteboard. Okay, welcome back everyone. So the first thing we need to do is determine the various pieces of information from this equation. So we can see the gradient of our line is equal to minus 1. And the intercept of our line is equal to 11. We need to find a and b. Well, we can see that a is equal to minus 3. Or rather, the equation should be x minus a, so we can see that a is actually equal to positive 3. My apologies. So a is equal to positive 3. B is equal to positive 5. And r is going to be equal to, well, let's think about this. Our equation usually has equals r squared. So r squared is equal to 9. R is equal to the root of 9. It's a radius, so it must be positive, so r is equal to 3. So here is our set of information. M's minus 1, C is 11, A is 3, B is 5, and R is 3. With this, we can now calculate A, B, and C. So we know that A is equal to 1 plus m squared, which is going to be equal to 1 plus minus 1 squared, which is equal to 1 plus 1, which is equal to 2. B is equal to 2cm minus 2a minus 2bm, which is equal to 2 times c is 11 times minus 1, minus 2 times a is 3, minus 2 times b is 5, and m is minus 1. So that's going to be equal to 2 times 11 is 22, times minus 1 is minus 22. 2 times 3 is 6, so minus 6. 2 times 5 is 10, times minus 1 is minus 10, times another minus is plus 10. So that's equal to minus 22 minus 6 is minus 28, plus 10 is minus 18. So B is equal to minus 18. And C is equal to a squared plus b squared plus lowercase c squared minus 2bc minus r squared. So that's going to be equal to, we saw a is 3, b is 5, so 3 squared plus 5 squared plus our intercept c is 11, so plus 11 squared minus 2 times b is 5, c is 11, minus our radius is 3, so 3 squared. So that's going to be 9 plus 25 plus 121 minus 5 times 11 is going to be 55 times 2 is minus 110 minus 3 squared is 9. So minus 9, which is going to give us 9 plus 25 is 34 plus 121 is 155. Minus 110 is 45, minus 9 is 36. So C is equal to 36. So again, A here is equal to 2. B is equal to minus 18. And C is equal to 36. With this information, we can use our quadratic formula to solve for x. So we know that we know that x is equal to minus b. So x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And we need to find the value of b squared minus 4ac to determine do the line and the circle intersect. So b squared minus 4ac is equal to minus 18 squared minus 4 times 2 times 36. Well, minus 18 squared is 324, minus 4 times 2 is 8, times 36 is 288. So 324 minus 288 is 36. This is positive, therefore their line does intersect the circle, and there are 2 points of intersection. So the next part of the question was to find those points of intersection. So x is equal to minus b is minus 18, so minus 18, plus or minus the square root, b squared minus 4ac is 36, divided by 2a, a is 2, so divided by 2 times 2. The minus and the minus become positive, so x is equal to 18, plus or minus the root of 36 is 6, so plus or minus 6 divided by 4. That means x is going to be equal to 18 plus 6 over 4, or 18 minus 6 over 4, which means that x is going to be equal to 24 over 4, or 12 over 4. And that means that x is equal to, well, 24 over 4 is 6, or 12 over 4 is 3. So x is equal to 6 or 3. We now put this into our line equation. Y is equal to minus x plus 11. So y is equal to minus x plus 11, which means it's equal to minus 6 plus 11, or minus 3 plus 11. Well, minus 6 plus 11 is going to give us y is equal to 5. Or minus 3 plus 11 is y is equal to 8. This means that our points of intersection are 6 in x, 5 in y, or 3 in x and 8 in y. Now if we were to draw this out, and I don't really have enough room here to really draw it, I suppose I could try and squeeze it in here. So if we were to draw this out, we would see, as I draw a little diagram, so we can see that y, our center point is 3 in x, 5 in y. So let's say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 3 in x, 1, 2, 3. 5 in y is the center point of our circle. It has a radius of 3, so that means we are going to extend, so that was 5, 6, 7, 8, up to 8 here. And 1, 2, 3, down to 2 here. We're in 3 in x, so we're going to extend right the way across to our y-axis here. And we're going to extend over here with our circle, so something like this. And our line is y equals minus x plus 11. So this is 0, 2, 4, 6, 8. We'd have, excuse me drawing over my formula, I didn't actually have as much room as I thought I did. Our intercept would be up here, and as we travel 1 in x, we're going to be traveling minus 1 in y. So that means if I was to come down 1, 2, 3, 4, we'd move over 1, 2, 3, 4. So that again was, if we are 8, 9, 10, 11 up here. And if we come down 1, 2, 3, 4, we'd come over 4. That gives us a line that's going to look something like this. You'll notice the points that it intersects through, obviously this is a rough diagram, but the points it intersects through are the top and the right-hand side of our circle. The top of our circle has an x of 3 and a y of 8. The side of our circle has an x of 6 and a y of 5. So 3, 8 and 6, 5. 3, 8 and 6, 5. So we can see indeed that our answer is pretty much correct. So in this video we saw a much more complicated example of how having geometric shapes in equation form can be incredibly useful to us. Just like intersecting two lines, we use the equations to find the point or points which satisfy both equations, and these points are going to be the points of intersection. Now, as I've mentioned a couple of times in this video, this method that we've shown here is the most obvious and immediate way to approach finding a solution to this problem. But as we've seen, even though the solution does indeed work and does give us the correct results, it is a little bit long-winded. There are quite a lot of calculations involved. So in the next video, we're going to take a look at how we can approach the problem in a slightly different manner and derive a method for solving these types of equations that firstly will be slightly more efficient, but more importantly than that, it's going to enable us to tackle problems where perhaps the generic form of the equation is extremely complicated, but their basic form, where there's some restrictions in place, for example, we're centered at the origin, the basic form is very simple. So it's going to be not only useful to us here in this particular example to give us a slightly more efficient way of working this out, it's also going to be a useful method to apply in more complicated situations. But this is going to conclude this video. Thanks a lot for watching, everyone.